Hi everyone! In this video we're going to be learning about hypothesis tests for a population mean. Previously we did this for our population proportion. So let's start with talking about test hypotheses about a mean. So testing hypotheses regarding a population mean, we can do this process provided the following are true. The sample is obtained using a simple random sampling or from a randomized experiment. The sample has no outliers and the population is normally distributed, or you could say the sample size is large, so 30 or more. And then the sampled values are independent, and the way we check that is to say that the sample size is less than 5% of our population size. So if all that's true, then we have our steps for testing our hypotheses about our population mean. So step one is to determine our null and alternative hypotheses. And then remember how this works. We've talked about this a few times. We can have our test structured as two-tailed, left-tailed, and right-tailed tests. Remember, H0 is our null hypothesis and H1 is our alternative hypothesis. Step two is to select a level of significance, which we call alpha, depending on the seriousness of making a type 1 error. And a lot of times you're going to be given what alpha is. And then step three, we're going to do this two different times because we have our classical approach, and then we're going to do it again with our p-value approach. So compute the test statistic T0. So what's different now from previously, we were working with our population proportion. Now that we're working with our population mean, this is T. Before it was a Z. So we're working with T, and remember our T distribution. We work with that when we use our sample standard deviation instead of our population standard deviation. So we calculate T0 just using our mean value from our sample minus our population mean over the standard deviation. So this is our standard deviation formula here, which follows students' T distribution with n minus 1 degrees of freedom. So we talked about our T distribution previously. And then we would go to our T distribution table to determine our critical values. And so if you have a two-tailed test, you have two critical values. And we've seen all this previously with our Z distribution. And so very similar here. For the two-tailed test, we take alpha and we divide it by 2. And so we get the corresponding T value, critical values, based on the area to the right under the curve of T sub alpha over 2, and the area to the left of negative T sub alpha over 2. For the left-tailed test, our critical value is negative T sub alpha, and for the right-tailed test, it's positive T sub alpha. Then step 4 is to compare the critical value with the test statistic, and based on the comparison, we can make our conclusion. So with the two-tailed test, we're trying to figure out if our test statistic T0 is less than the negative critical value or greater than the positive critical value. On the left-tailed test, if T0 is less than our critical value, and on the right-tailed test, if T0 is greater than our critical value. In all those cases, we would reject our null hypothesis. If we didn't get that those were true, we would say that we don't reject the null hypothesis. Remember, we don't say we accept it, we just say we don't reject it. And then step 5 is to state our conclusion. So starting over at step 3 real quick, using the p-value approach, same step 3, compute your test statistic T0. Then we go to our T distribution table, and then this time what we want to do is we want to get our p-values. So we have our p-value for the two-tailed test is actually 2 times the probability that T is greater than T0, our test statistic. Okay, so we have to compute that one. For the left-tailed test, our p-value is the probability that T is less than our test statistic. And then for the right-tailed test, our p-value is the probability that T is greater than T0. And then if we use do step 3 with technology, you don't necessarily have to use the table we were just talking about, but you can use StatCrunch, a calculator, Excel, lots of technology to get that p-value. And then step 4, we just say, is our p-value less than alpha? And if it is, we reject the null hypothesis. And then we state our conclusion. Okay, so notice that the procedure just presented requires either that the population from which the sample was drawn be normal, or that the sample size be large, greater than or equal to 30. That was one of the first things we talked about when we began. So this procedure is considered robust, meaning that minor departures from normality will not adversely affect the results of the test. And however, if the data included outliers, the procedure should not be used. So just a caution here. Okay, so let's try out an example. The mean height of American males is 176.3 centimeters. The heights of the 44 male U.S. presidents, Washington through Trump, have a mean height of 180.1 centimeters with a standard deviation of 7.1. Treating the 44 presidents as a simple random sample, determine if there is evidence to suggest that U.S. presidents are taller than the typical American male. And we're going to use alpha equals 0.5 for our level of significance. Okay, so step one, we're trying to figure out if U.S. presidents are taller than the typical American male, which we knew was 176.3 centimeters. So we assume there's no difference between the height of a typical American male and the U.S. presidents. So that is our null hypothesis. That's why it's H naught. So mu equals 176.3. And so our alternative hypothesis, what we're trying to figure out is if U.S. presidents are taller. So we're trying to figure out if mu is actually greater than this 176.3. And then we know our level of significance, alpha was given as 0.05. So then step 3 with the classical approach. Okay, so we know our sample mean x bar is 180.1. Standard deviation S was from our sample, so it's 7.1. And so if we calculate our test statistic, T naught, we get 3.550. Okay, and so this is going to be a right-tailed test because of our alternative hypothesis. We're looking for mu greater than our null hypothesis value. And so what we want to do is, based on our critical value at alpha equals 0.05, we have to use our table, and then remember the degrees of freedom when we're using t-distribution comes into play. So we were told that we have a sample size of 44, so the degrees of freedom is always n minus 1, so that's why it's 43 degrees of freedom. And so t sub 0.05 is going to be 1.684, and this is actually using 40 degrees of freedom from our table. And so let me show you on the table how we got that value. So here's our t-distribution table, and we are going to line up the degrees of freedom row with our 0.05 column. So let me just go down from here. So 0.05, and if you notice, after 40, the table actually skips degrees of freedom by 10. So that's why we pick 40, because 43, our degrees of freedom, is closest to 40 on the table. And that's why we're going to get 1.684. So because our test statistic T naught was 3.550 and it's in the critical region, or another way to say that is because T naught was greater than our critical value, we reject the null hypothesis. And so we can say that there's sufficient evidence at the 0.05 level of significance to conclude that U.S. presidents are taller than the typical American male. So let's do it again using our p-value approach. So we have the same sample mean and standard deviation. We get the same test statistic. T naught is 3.550. Okay, so now what we're going to do is we're going to go to our t-distribution table, and we know our test statistic T naught is 3.55. So we're going to look for the critical value closest to this. Okay, so here's our table, and I have it highlighted here for 40, which is the closest degrees of freedom this table has to 43. We had 3.550, which is in between these two numbers. Notice it's actually much closer to the right one, 3.551, than it is to 3.307. But we're going to say that our number our test statistic is in between these two. So from there, let's go up. And then that means the area of corresponding to our test statistic, or the probability that we're looking for, is between 0.001 and 0.0005. Or this one's actually smaller. So between 0.0005 and 0.0001. Okay, so then our 3.550 lies between the two numbers we found from our table. And we have the areas corresponding to those two critical values. And so what we would say is that our p-value is between those two probabilities, or those two areas, between 0.0005 and 0.001. So if we go to StatCrunch, we can get that the p-value is actually 0.0005. And so let me show you real quick how to do that. So in StatCrunch, we're going to go to Stat, and let's go down to T-Stats, and I want one sample, and we're going to go with Summary. Okay, so we know our sample mean was 180.1. The sample standard deviation was 7.1. Then our sample size was 44. And let's put in our null hypothesis that mu equaled 176.3. And our alternative hypothesis was that mu was actually greater than that. Okay, and then if I want to get the graph, I'll put that there. And let's compute. Okay, so here is our summary, and here's our p-value. And if you wanted to see the graph, it's right here. And notice we're way over here to the right side. All right, so let's see what that means. We already actually know from our classical approach, but because of our p-value of 0.0005, that means that if the null hypothesis is true, we expect the sample mean of 180.1 or higher in about 5 out of 10,000 samples, because this is 5 10,000s up here. And so the results we obtain do not seem to be consistent with the assumption that the mean height of the population is actually 176.3. So another way to say that is because the p-value is less than the level of significance, our p-value is less than alpha, we reject the null hypothesis. And so we conclude there's sufficient evidence at a 0.05 level of significance to conclude that U.S. presidents are taller than typical American males. Okay, let's keep going. Let's try another one. The fun size of a Snickers bar is supposed to weigh 20 grams. Because the penalty for selling candy bars under their advertised weight is severe, the manufacturer calibrates the machine so the mean weight is actually a little bit more, 20.1 grams. The quality control engineer at M&M Mars is concerned about the calibration. He obtains a random sample of 11 candy bars, weighs them, and gets the resulting data. Should the machine be shut down and calibrated? Because shutting down the plant is very expensive, he decides to conduct the test at a 0.01 level of significance. So recall that the level of significance is the probability of making a type 1 error, which is when we reject the null hypothesis, even though it's true. And so anytime the consequences of making a type 1 error are severe, you want to pick a small alpha value, a small level of significance. So just a reminder about that. Okay, so here we have our normal probability plot as well as our box plot. So if you recall, we're going to look at these two things because we're trying to verify that our sample data appear normal enough before we can technically use our t-distribution. So we've talked about this previously when we were doing estimating a population mean, but let me go back through it with you real quick. And so we're going to go over to StatCrunch and create both of these graphs and determine our correlation coefficient, which is going to be this 0.967, or it's actually going to be 0.90 with technology. And we compare that to our critical value, if you recall from the past, to figure out if our data is approximately normal, which in this case it is. So let's go over to StatCrunch real quick. Okay, so in StatCrunch, I've already inputted our raw data. So let's get the box plot first. So I'm going to go to Graph, Box Plot, and our variable 1, and let's draw our boxes horizontally, and that should be good to go. Okay, and what we're looking for with the box plot is if there's any outliers. Let's also do our our probability plot. So we're actually going to go to graph QQ plot, select our column. I'm going to put the correlation statistic on there. Let's go ahead and check normal quantiles and compute. Okay, and so this is just for us to verify that our data is approximately normal or normal enough so we can officially use our t-distribution. And so we have this correlation coefficient of 0.97 right here. And so we compare that to our critical values. Let me take you to that table real quick, which is right here. And so for our sample size of 11, that's why we are comparing that value of 0.97 to 0.923. And so because it was greater, we can claim, and because there's no outliers, we can claim that our data was normal enough and use our t-distribution. Okay, so now we can proceed to the hypothesis test. So for our hypotheses, the null hypothesis is that the mean is actually 20.1 grams, and then the alternative hypothesis is just that it's different. The mean is different from the 20.1 grams. So we are going to be working with the two-tailed test. And then our level of significance we've determined should be pretty small, 0.01. And so using our classical approach, if you just use your raw data and you compute the mean, you're going to get your sample mean is 20.301, and your standard deviation is 0.64 grams. And so your t-value, plugging in those numbers in, is going to be 1.042. Okay, so for our two-tailed test, remember we divide alpha by 2. And so our critical values are at negative t sub 0.005 and positive t.00 sub 0.005. And so with 10 degrees of freedom, since our sample size was 11, and going to our t-distribution table, that's how we can get our critical values are negative 3.169 and positive 3.169. And then notice where they're at. The critical regions are here and here. And our t-value, our test statistic, is actually right here in between them. It's not in either one of the critical regions. And so because our t-naught value is not in one of the critical regions, it's not less than the smaller critical value or greater than the bigger critical value, we do not reject the null hypothesis. So we can conclude there is not sufficient evidence to conclude that the Snickers have a mean weight different from 20.1 grams at a 0.01 level of significance, so the machine should not be shut down. Okay, same problem, but just doing our p-value approach. So we got our sample mean and standard deviation from our raw data. Our test statistic is still 1.042. And now for our p-values, remember we're looking for probability here. And so we have negative t-naught is negative 1.042, and then t-naught is still positive 1.042. And so remember how this works with the two-tailed test. Our p-value is actually twice the probability that t is greater than 1.042. And we're working with 10 degrees of freedom. Okay, so using our t-distribution table, we'll find the row corresponding to 10 degrees of freedom. And then our t-naught value was 1.042. And what we're going to see is that lies between the two closest numbers as 0.879 and 1.093. And then we'll find the areas corresponding to those two, and that'll help us get our p-value. So let's go jump over to our table real quick. Okay, so we have our t-distribution, and for 10 degrees of freedom, our t-value was 1.042, which is in between these two. And so if we go up, the corresponding areas in the right tail are 0.2 and 0.15. And so because this is a two-tailed test, we're going to double those values. Okay, real quick, let me go over to StatCrunch also to show you. But our p-value is going to be between 0.3 and 0.4 if we double these values. So let's see in StatCrunch. I'm going to go to Stat, and let's go down to T-Stats. Let's do one sample, and this time with data. and we're going to select our column with our data in it, and our null hypothesis was equal to 20.1, and our alternative was that mu was not 20.1. And let's compute. And so see what our p-value is with technology, 0.3226. Okay, so we already have our p-value from StatCrunch, but I want to show you this other table that has a little bit more detail. It's a t-distribution table. We can be a little bit more precise here. So the degrees of freedom for us was 10. So if we go down the 10 column, and our t-value is 1.042, so the closest one for that is 1.0. And so if we line that up with our degrees of freedom, our probability or area under our curve is right here. It's the 0.170. Okay, so we figured out that p was between 0.3 and 0.4 because we doubled the values from our table. And then from the other table, we are looking at t greater than 1. And so we just say 2 times that probability. So 2 times 0.17, and we get 0.34. Then with technology, we got that our p-value was actually 0.3226. And so the p-value of 0.323 means that if the null hypothesis of 20.1 grams is true, we expect 32 out of 100 samples to result in a sample mean as extreme or more extreme than the one obtained. The results we obtained is not unusual, so we do not reject the null hypothesis. And we conclude there's not sufficient evidence to conclude that the Snickers have a mean weight different from 20.1 grams at the 0.01 level of significance, so the machine should not be shut down. Okay, our last objective for this one is going to be to understand the difference between statistical significance and practical significance. And so practical significance refers to the idea that while small differences between the statistic and parameter stated in the null hypothesis are statistically significant, the difference may not be large enough to cause concern or be considered important. So that's practical significance. Even though there are small differences between our test statistic and our parameter value in the null hypothesis, it might not be a large enough difference to be of a concern. And so here's an example. According to the American Community Survey, the mean travel time to work in a certain county in Texas was 29.3 minutes. The Department of Transportation reprogrammed all traffic lights in an attempt to reduce travel time. To determine if there is evidence that travel time has decreased as a result of this reprogramming, the department obtains a random sample of 2,500 commuters, records their travel time to work, and finds a sample mean of 20.9 minutes, with a standard deviation of 8.5 minutes. Does this result suggest that travel time has decreased at the 0.05 level of significance? And so our null hypothesis would be that mu is the 29.3 minutes versus the alternative that the average travel time to work is actually less than that. And our level of significance was 0.05. Okay, calculating our T0 value, plugging in our values, we get negative 1.765. And using our classical approach, this is a left-tailed test based on our alternative hypothesis. And so we have our degrees of freedom is 2499, and our critical value is actually negative t sub 0.05, which is negative 1.645. And if you go to your t-distribution table, you're going to go up to the degrees of freedom that says 1,000 or more. And so because the test statistic is less than the critical value, our test statistic was negative 1.765, we reject the null hypothesis. And so using our p-value approach, we want the probability that our T0 is less than negative 1.765. And then from our table, we can use the approximation that p is between 0.05 and 0.025, or we can use technology. We would get the actual p-value is 0.0389. And then similarly, we'll get the fact that because our p-value is less than the level of significance, we also reject the null hypothesis. So to conclude, there is sufficient evidence at the 0.05 level of significance to conclude the mean travel time to work has decreased. And so while the difference between 20.9 minutes and 29.3 minutes, or sorry, 29.0 minutes and 29.3 minutes is statistically significant, it really has no practical meaning. And so after all, if you think about it, 18 seconds isn't really going to make anyone feel any different about their commute to work. So this was an example of practical significance, and even though our results were statistically significant, practically it didn't really make a difference. And so last, we'll just mention that large sample sizes can lead to statistically significant results, while the difference between the statistic and parameter is not enough to be considered practically significant. So this is just something to be aware of when your sample sizes are very large. Okay, that's it for this one. Thanks for watching.